All right, so we're going to talk about antiderivatives today. The word antiderivative, the way we use it, and the phrase indefinite integral, those are going to be synonyms. So I'm going to use those kind of interchangeably when I say that we're going to work with an antiderivative, or we're going to learn about finding antiderivatives, or if we say that we're working with what's called an indefinite integral, same thing. Okay. I will be lazy. I will be just kind of saying integral, wherein I mean indefinite integral. And if you're like, well, why is it indefinite? Because indefinite integrals, we're not doing any areas. And you can tell we're doing an indefinite integral because if you look at all of the integral problems, or the things sitting next to the integral signs, there's no a and b at the top and bottom. Okay, so that's the biggest clue that we're sort of in something a little different. It's the same symbol, but we're using it a little differently. We're using it to indicate I want to find this thing called the antiderivative. And there's really no other symbol that we have out there that use it. Derivatives have lots of symbols, like find y prime, find dy dx, find the derivative, find the rate of change, find the instantaneous rate of change, all those different, slope of the tangent line, all those different things meant, hey, find the derivative. There's not as many things that mean find the antiderivative. It's kind of like antiderivative, indefinite integral, or using the integration sign next to the expression. Okay, so when I write an integration sign next to an expression, like let's say I wrote this. Okay. I know it's not an area because it doesn't have any numbers at the top and the bottom. What this is asking me is to figure out the function, or find a function that has 2x as its derivative. Or another way to think about that is f prime of x is 2x, so f of x equals what? Everybody's favorite. We're kind of going backwards, at least backwards from what we're used to doing with derivatives. We're undoing the derivative work. Now, there are so many complicated ways to do derivatives that the number of complicated ways to figure out antiderivatives is like 30 times as many. And even if you were in a Calc AB course, even if you were in a Calc BC course, even if you were in a multivariable calculus course, you still would never be able to learn every potential antiderivative derivative combo. There's just so many ways to make derivatives. It's almost impossible in some cases to figure out without a lot of extra help what the original function looked like. And honestly, if you look in the back of a calculus textbook, usually there's a table of antiderivatives or indefinite, usually they call it the table of antiderivatives. Where is this one? And it's like 4 or 5 pages long. It's got like 140 some entries in it. I'm trying to find that in here. Where's my antiderivative table? I should have marked it. There's the glossary. There's back of the book answers. Check Bob. And I think it's actually, there it is. Okay. So yeah, I think the people who write books are just like sort of like low-key given shade because they call it a brief table of integrals, and it's 1, 2, 3, 4, 5, 6 pages long. It has 141 different options, and that's just a brief table. Okay. So I'm not telling you that to scare you. I'm telling you that so you know what we're going to learn about integrals and antiderivatives is like this much. And even in people in AB learn about this much, and people in BC learn about this much, because there's like this much out there. Okay? Antiderivatives are tough. But for polynomial type functions, just like how derivatives were kind of easy, antiderivatives are easy. If the derivative is 2x, talk to me about the original function. What do you think it was? It was probably x squared, right? I mean, that kind of, if you use what we know about how functions work, how functions in basic derivative work, f of x equals x squared would be a possibility. So I would say that the antiderivative or an antiderivative of 2x dx is x squared. Now, first of all, don't freak out because you're like, so what? Am I just supposed to like, no, there's a trick. I start with this one because this is one we can usually undo in our head, just like we can do that derivative real easily in our head. But there is a process for helping us figure it out. But before we even get into the process, I need to add another little sort of spin to this. We wrote down that the antiderivative for 2x dx is x squared. And that's true because if I took the derivative of x squared, I would get 2x. Okay, so I'll make a little note here. How do I know this is right? I know because the derivative of x squared is 2x. But what if I wrote x squared plus 5 instead of just x squared? Because I'm just like that. What's the derivative of x squared plus 5? Derivative is 2x. Oh, and that's all I need. So that's a good answer, but that's a good answer. Is that a good answer? Is the derivative of x squared minus root 56 equal to 2x? Yeah, even though this is like, you're like, well, you made that look scary, but it's still just a constant. You know, root 56 is just a constant. So the derivative of x squared plus or minus any constant still has a derivative of 2x. So how do we address that? Well, originally, and the first thing we do is we just kind of go, okay, I know most of the original function, but I'm going to put sort of a little unknown little piece on the end. The antiderivative for 2x, I will say, is x squared plus c. And plus c, that just stands for some constant. There may have been a mystery constant sitting with the x squared plus 5, x squared minus 10, x squared plus 37, x squared minus 246, x squared plus the cube root of 73, whatever. Some mystery constant sitting with the x squared that when I took the derivative, I just ended up at 2x. I'm going to ultimately be able to figure out mystery constants if I have other information. For today, we're not going to have any additional information. I just have to go, well, there's a chance there's some constant attached to my antiderivative, and so I gotta account for it. And so every time we write an antiderivative, that's what goes on the end, plus c. Now, it doesn't technically have to be a c. We use a c for constant, and I always forget this. This is like the first year I remembered it actually when I'm teaching it. Later on, when we do application problems with this, since c is cost, a lot of times in business problems, instead of using plus c for antiderivatives, they'll use plus k. So if you want to like do plus k instead, you can. It's just another, it really could be any letter you wanted. It just represents that, hey, there's another chunk of function attached to this thing that I don't really know what it is. It could have been there, it couldn't, it may not, I'm not sure. I need more information. If you ever look up calculus memes, because, you know, I know that you love to look up calculus things. If you look at calculus memes, a lot of times you'll see ones about, like, remembering to put the plus c. Technically, when you write an antiderivative, if you don't write the plus c, it's wrong. So, like, the baby that's like, yeah, so he's like, remember to put the plus c, and you'll see a lot of calculus memes that talk about doing the plus c. It's sort of one of those things with an antiderivative. Okay, so what do we know so far? We're going to be going backwards. We're going to go from a derivative to a function, and we're always going to write a plus c after our antiderivative. So that's like a universal thing that we'll have on all of our answers. Let's take a look at the first few problems. And we're going to use these first few problems to kind of introduce some of the rules. Okay. We're finding a general indefinite integral. We're finding an antiderivative. All right, rule 1. Constants. Constants just sitting there. Well, if my derivative is 7, my function must have been 7 times a variable. The dx that's there tells you what variable to use. It is possible to have integrals have double integrals and integrals in terms of 2 different variables. That's kind of one of the things that happens in a multivariable calculus class. So for us, it's always going to be kind of like, well, yeah, I'm going to do x, but it might be t or something, but we're never going to have like different ones. It'll just be one letter. So antiderivative of 7 is 7x plus c. Write that again in a prettier way. 7x plus c. You know you're right if you take the derivative of your answer and you get back to this guy called the integrand. He's the thing sitting next to the integral. The derivative of 7x is 7. When I take the derivative in terms of x, the derivative of a constant is 0. So 7x plus c has a derivative of 7. 7x plus c, as my son would say, good job. Thumbs up, good job. That's the function I'm looking for. Now, powers. Think about what we do a derivative. And we're going to reverse those 2 things. Okay. So when I take a derivative, I multiply with the exponent and then subtract 1. So my derivative process is a multiplication step and a -1 step. I'm actually going to write that down. When I take a derivative, with a power rule, I multiply by the exponent and then subtract 1. So when I take the derivative of x to the n, I get n times x to the n minus 1. You know, we've done that about a bazillion times since I first taught it to you, I don't know, October? Okay. So antiderivative, I'm going to do the opposite of these two things, and I'm going to do them in the opposite order. I am going to add 1 onto the exponent. I should have written that from exponent. And then I am going to divide by that new exponent. So the way that's going to look in symbols, when I take the antiderivative of x to the n, that's going to give me x to the n plus 1 divided by n plus 1 plus c. Derivatives take a multiplication step with a subtraction step. Antiderivatives take an addition step. Your exponent gets bigger by 1, not smaller, and you divide. So if we try that, that means x to the 5th antiderivative is going to become x to the 5 plus 1 divided by 5 plus 1 plus a big old c. Or, let's make it prettier. How about x to the 6th over 6 plus c. Now, you absolutely right now are like, no, yes, you can do this. You didn't think you were going to be able to do derivatives, and then you did derivatives, and you did product rules, and you did quotient rules, and you did e's, and you did natural logs, and you did chain rule, and you did all kinds of crazy stuff with derivatives that it didn't look like you were going to be able to do until we did it like a bazillion times, and then you're like, okay, yeah, I can do it. Same thing here with antiderivatives. It's uncomfortable because this is the first time we're doing it. The more we try it, the more we practice it, the more it'll be a muscle memory, because our brain is just a muscle. So anything we learn to do physically, same thing mentally, muscle memory. Add 1 to the 5 and divide by that new number. All right. So let's do number 3. Just like when we do derivatives, when we do antiderivatives of sums and differences, we can do them in pieces. So when I want you to do number 3, I want you to think about it as doing the antiderivative of x to the 4th dx minus the antiderivative of x squared dx. Okay, see what you would write for that. Try it yourself. Follow the rule. Look back. If you need to look at the rule, I'm going to actually write the rule. Just like I used to with the derivative rule. I don't know why I do my ones different ways to glitch in my brain. Sometimes I just write once and then you're probably going to ask me something about something on your answer, and we'll talk about it. You're going to think like, I don't know, what do you want me to do with all the letters. Ooh, who's calling me? No clue. Don't know that number. And if they're calling me in the middle of the day, they probably don't know me. Oh, and I'm recording that. That's the fun part. You get like the outtake. You have Mrs. Bowenbach just like randomly talking about stuff. All right. Okay. We'll finish doing this problem and then I'll probably stop the recording for a little bit. All right. Now, one of the things that happens in Calc AB and BC is you learn derivatives and integrals kind of mixed together. You do some derivatives and then you do some antiderivatives and then you do derivatives and then you do you kind of go back and forth. So your friends who are in AB or BC learned to do this early, a long time ago. It's just different order. It's definitely harder to go back and forth, and they have to be able to do that. So that's why we do teach it that way. Because we're prepping them for a specific exam that has problems that have both types of things in one question. We don't have to do that, so we can talk about them separately. But my point is, your friends who are in AB or BC can absolutely help you with this if you're, need sort of extra help out on the side. X to the fourth, antiderivative, x to the fifth over 5, plus a c. I'm gonna put a little 1 next to that c, because when I do the next antiderivative and I write plus c on that one, I don't know that those c's are the same. So I've got to make sure I differentiate between them. Some textbooks will have you write a D. I like C's with little subscripts. And what we typically do then is, you don't know that these C's are the same. So you don't know that they're going to cancel out. But you do know you could combine them in some way. You don't know what the result's going to be, but it's going to be some combination. And so usually what we do mathematically, this is the whole mathematicians are lazy, is you're like, all right, I'm not going to write all those multiple C's in one problem. I'm just going to write me kind of one big generic C. So technically, each antiderivative piece generates a possibility of a constant. When we write the final answer, we combine those into one big universal generic C. So when I do this problem, you will not see me writing multiple C's. I'll just go, x to the fourth, x to the fifth over 5, x squared, x cubed over 3, did all the, shove a plus c on the end, and I'm done. Okay.